When we talk about conductors, the image that goes into our brains is charges moving from one side to the other, right? All conductors support conduction of charges, the movement of charges. But how do conductors behave if you were to place a static charge on them? In other words, the charge is confined to the conductor. The excess charge exists on the conductor, but it is not going anywhere else. Well, the picture is slightly counterintuitive. It may not agree with the logic that we have seen so far. So let's understand what happens. Let's say that we have a conductor. So it has no definite shape. It's not a cube, it's not a cylinder, it's not a sphere. It is just a amorphous material, which is a conductor. And we have provided this conductor with some excess charge. So let's say that I have given it a few extra negative charges. So here are these negative charges. What we are trying to understand is how will these excess negative charges, which are causing an imbalance of charge inside this conductor, behave inside this conductor? Will they move away from each other? Will they move in one direction? Where will they come and stop? All of these things we are going to understand. The excess charges here are all of the same sign. So we know that all like charges will repel each other. The other thing that we remember is that conductors allow the movement of charges inside them. That is the main property of electrical conductors. They allow the free movement of charge inside the material. So since all of these electrons hate each other, they are repulsive, they want to move away from each other, these excess electrons will try to move away. And since they can move freely inside a conductor, they will all move until they have reached the surface of the conductor. So all of these charges will now be at the surface of the conductor. And this behavior of charges, of excess charges inside conductors, gives us some important results. The first result is the electrical field inside a conductor for electrostatic cases is equal to 0. So there will be no electrical field inside the material, inside the bulk of the conductor in the electrostatic case. The reason for this is that if you think about Gauss's law, if you think about the electrical field generated by an amount of charge, the electrical field is proportional to the charge enclosed by a given volume. So in this case, since all these electrons have moved to the outermost surface of this material, so the electrons are no longer inside the bulk of this material. They have all moved, the excess charges have all moved to the surface of the material. So they reside only at the surface of the material. Please note, we are talking only about the excess negative charge. We are not talking about the electrical charges already inside the conductor from before. Because all of these excess electrons are now at the surface of the conductor, if you took any arbitrary volume inside this conductor, there is no excess charge. Repeat, there is no excess charge enclosed inside these volumes. And since there is no excess charge enclosed by these volumes, the electrical field inside the conductor in the electrostatic case will be 0. The next result that we understand from this behavior is that since these electrons are moving away from each other and are at the surface of the conductor, if we were to divide the surface area into smaller area elements, so I can break up the surface area into smaller area elements, I will notice that the electrical fields at those points will be perpendicular to these areas. The electrical field will always be at 90 degrees to these area elements. And the reason for this is simple. Let us say that the electrical field is not perpendicular. So here you have an area element, and let's say that the electrical field is not perpendicular, it is at an angle to this area. That would imply that there is a vertical component of this electrical field, Ey, and there is a horizontal component also of this electrical field, that is Ex. If there is a horizontal component of this electrical field, then the surrounding electrons in that region or the surrounding charges in that region will experience a sideways force. So they will move under that sideways force, and they will move long enough so that the forces become equalized everywhere. All the excess forces become equalized. All the electrons are now in positions where they have no further potential. This means that in the electrostatic case, once the system has stabilized, all the electrical field lines coming out of these surfaces will be perpendicular to the local surface. The next thing that we have to understand, so we understood that the electrical field inside the conductor is zero. We understood that the electrical field is perpendicular to the local surface. What's next? Well, there will be no excess charge inside the conductor. It does not matter how much excess charge you pour into this conductor using whatever method that you know about. In the electrostatic case, all of that charge that you are pouring into this conductor will immediately move to the outermost surface. So for any conductor, the amount of excess charge inside the bulk of the material will be zero. So there is no excess charge inside a conductor. So this is the fourth result that we have. The last result that we get from this behavior is that there is no potential difference anywhere inside this material. The potential, electrical potential at all points inside this material, the difference in potential for all points inside this material is equal to zero. Now think about why this is the case. Potential is the ability of charges to do work. If you were to put excess charges in this material, as we reviewed earlier, all the charges will get away from each other, as far away from each other as possible, until an equilibrium is reached. They cannot leave the material, but they will arrange themselves on the surface of the material in such a way that no further movement is possible. All the charges are at their minimal energy. There is no change in the potential of charges anywhere in this material. So the potential differences inside this material will be zero at all points. And this property that we have understood for the behavior of static charges in conductors also has certain very important real-world applications. For example, there is a device called a Faraday cage. It is nothing fancy. It is just a mesh or a net of conducting material that you can place around sensitive instruments. What this material does is that if any excess charge is encountered in the local environment, let us say that you have built a spacecraft which is traveling to Jupiter. So Jupiter has a large amount of excess charge in its upper atmosphere, and that excess charge can damage the devices inside that space probe. So what do? You cover these instruments with a fine mesh of gold or a highly conductive material. So what will happen? Any excess charge which is encountered by the space probe, this charge will accumulate on the outer surface of the Faraday cage. The potential inside will be zero, the electrical field inside will be zero, which means that the delicate electronics in these probes, in these devices, will remain unaffected by the excessive electrical fields outside. So the fact that there is no electrical field inside a material in the electrostatic case has profound implications in the real world. Also, you could ask, sir, under what circumstances could you get electrical fields inside a conductor? Well, if there is a steady current flowing inside a conductor for a period of time, in that particular case, it is no longer an electrostatic case. It is a case of current electricity, in which case you will have a definite electrical field inside the material. So the statement that there is no electrical field inside a conductor is valid only when we are considering electrostatics.
Manorama Horizon. Learning made simple.